balancing equations. Now you guys, go ahead, did you start? Oh, by the way, today is Tuesday, February the 23rd, advanced level chemistry. Again, feel free to subscribe to my channel. I'm up to 80, and so shoot for 100. These exciting, you're gonna want to be a part of this unit. Okay, so we want to write balance equations. You probably did this some in 8th grade, you balanced equations. So this is going to be today just a quick review of that. It should be something that's relatively easy for you. Then we're going to practice taking a word equation into a formula equation. That's where we're going to use all of what we learned naming and apply the naming and then put the compounds together to make a reaction. Once we get to that, then we're going to go and we're going to look at, okay, well, we have 5 different types of reactions. Does anybody know the different types of chemical reactions? Did you learn that in 8th grade? Like a composition or synthesis?
We did, but
we like some of the words. We didn't
really.
Decomposition. Not ringing any bells? Single replacement.
I'll just read it off the next
page. I was going to give you some kudos there for remembering. Okay, so let's just start by when we look at the steps for writing and balancing an equation. All right, the first thing you're going to have to do is determine the correct formulas for all the reactants and products. Okay, that's where our naming is going to come into play. So if we have an equation that, you know, I say silver nitrate plus calcium chloride and how do we read the arrow? Yields or goes to? Okay. And what do you, any guesses as what do you think that would mean? Okay, so let's just do this part. Silver nitrate, what's the formula of silver nitrate going to be? So this is where we're going to have to determine the correct formulas.
AG.
Yeah, very good, AG. And you look on the periodic table, and you're not going to have to know this. You look and there's a little number 1 above the symbols for AG. So I know it's +1. And then you look on your chart and you see that nitrate is -1. So it's just going to be 1 to 1. So determine the correct formulas for all the reactants and products, balancing oxidation numbers using subscripts. That's what we did all about chapter 7, writing and balancing equations. Plus, what's calcium chloride?
CaCO2.
Okay, because Ca is going to be what charge?
+2.
And chloride we know is -1, so it's going to be CaCl2. Now that's going to yield silver chloride plus calcium nitrate. So
you just switch the 2 metals around?
yep. Okay, so silver chloride is going to be what? AgCl. Doesn't matter that it's a 2 here. We're going to balance the charge first with subscripts. So we're going to say Ag, which is +1, and Cl, which is -1. So it's just AgCl plus calcium nitrate. Well, what's calcium's charge? +2, so it's going to be Ca2+. What's nitrate? NO3 -1, right? So what do I do there? No.
2 nitrates.
I need 2 nitrates. Because I have a +2 and a -1. I have to balance the formulas first, balancing my oxidation number. So what's the formula going to be? NO3 in parentheses, 2. So we have to write the formulas correctly the first time, balancing oxidation numbers. Doesn't matter if it's a 2 here, that doesn't make it a 2 there. Doesn't matter if it's a 1 here. You balance the charge first with the subscripts. We'll come back and balance atoms afterwards with coefficients. Okay? So write the formulas for the reactants on the left side. So we know that this is just basics. This is reactants, right? These are your products. I mean, that's hopefully something that you're pretty much already aware of. Okay? If 2 or more reactants or products are involved, separate the formulas with plus signs. Okay, so that's just, I mean, that almost is almost embarrassing to put that simple thing up there. So then we go to 3. Count the number of atoms of each element in the reactants. A polyatomic of ion appearing unchanged on both sides is counted as a single unit. So this means we're going to balance it. So I'm going to count. I got 1 silver here. This is your equal sign. This is going to be balanced. 1 silver, 1 silver. This is my polyatomic ion, the nitrate. This is what this is saying right here. If a polyatomic ion is appearing unchanged on both sides, so you have a nitrate there. The nitrogen and oxygen didn't break apart. Okay? So I can just count those. So I have 2 nitrates here, but I only have 1 here. Now I've already balanced my charge, so I can't change subscripts. I balanced atoms with coefficients. So I'm going to put a 2 out in front. But now that gives me 2 silvers. So I come back here and I put a 2. It's always out in front. You never put the coefficient in the middle of the compound. We just did all the naming stuff. We never saw a coefficient in the middle of a formula. But now that gives me 2 chlorines, but looky there, I have 2 chlorines. Now this bad boy's balanced. So we could say aluminum plus sulfuric acid yields aluminum sulfate plus hydrogen. So what's aluminum going to be? Well, it's going to be Al, but this is just aluminum metal. So it's just going to be Al. Elements in their natural state, when they're pure, are all neutral. They're only going to have a charge when they're combined with something. Okay? So it's just going to be Al. Sulfuric acid came from which anion? Sulfate, okay, which we look up here to be SO4 with -2. Since it's an acid, what's the positive thing going to be? So the formula is going to be H2SO4. Good. That's going to make aluminum sulfate. So aluminum is what charge? Now it's combined, so it's going to be +3 or 3 plus. Sulfate is SO4 2 minus. Crisscross, so we're going to put a 2 and a 3, right? Plus hydrogen. What's hydrogen? Just hydrogen going to be? H2. So now we have to balance this. 1 aluminum, 2 aluminum. I got to put a 2. 2 hydrogens, 2 hydrogen, but I have 3 sulfates. Notice the SO4 is not changing, so I don't have to do sulfur and oxygen by themselves. I can just do 3 sulfates. So what do I do? Put a 3 out in front here. That means I had to put the 3 on the hydrogen. That's exactly right.
I remember when we did one of these, our 8th grade teacher tried to make it as long as possible. Or like, no matter what you did, you had to keep going and going.
Back and forth,
Just
they
over and
constantly
over.
changing.
We used like a
Well,
whole sheet.
we'll talk about some of the ways to make it not quite that challenging. Okay, so let me give you one more. Sodium metal plus water yields sodium hydroxide
So he was like,
plus hydrogen.
wait, Mr. Hobbs, I thought pure sodium blew up in water.
It does.
Oh, okay.
It's the hydrogen gas that gets produced that is highly exothermic. I mean, the reaction is highly exothermic, so that there's enough heat that that hydrogen gas catches on fire. So, sodium metal, what's it gonna be? Na. But I'm gonna put an S right there. What is that S gonna imply?
Solid.
Solid. Water obviously is H2O. And what state is it gonna be? Liquid. And how do you think we represent that?
Swervy L.
With an L. It's gonna go to a solution of sodium hydroxide. What's sodium hydroxide gonna be? Sodium is what? Na. Hydroxide, that's a plus. Hydroxide is OH minus. Now don't guess, because you're always gonna have this. Okay, you'll have the sheet, you know, to be able to look. So don't just guess what the ion is. Take your time to look it up. So it's just NaOH. Now it's gonna be a solution. Does anybody know how we represent something that's dissolved in water? Very good, aqueous, AQ. Okay, it's kind of from the Latin aqua. Aqueous means something dissolved in water. Since water is used so often for things to be dissolved in, they have the AQ. So the difference between these two, this is just salt like on your table in your salt shaker. This is solid salt. But this is like salt like in the ocean or the Gulf, okay? Salt dissolved, or the salt you put in your spaghetti, you know, in the water to boil your spaghetti noodles. Or if you have contacts, the saline solution is salt dissolved in water.
Yeah, so how come that salt doesn't burn your eyes?
Because they probably add stuff into it to keep it from doing that. I don't know. I've never had to do it, so.
Contacts on the phone, so.
Yeah, I know. And then hydrogen, what's hydrogen gonna be?
H.
H2. And what state is it gonna be?
Yeah.
It's gonna be a gas, which is gonna be a G. So just make sure that we know that this stands for liquid. This stands for aqueous, which means dissolved in water. And G stands for gas. Again, those things, hopefully all this is reviewed. But I'm still just putting it out there for you, so we're just making sure there's no stone left unturned. Okay, so that's just balancing equations. Now, did we balance this one? No.
Wait.
One sodium, one sodium. Two hydrogens, but I have three hydrogens. Okay, now notice hydrogens are here, here, and here. So leave that, if something is in more than one place on each side, leave that to the end. Okay? I have one oxygen. Okay, so I have to just deal with my hydrogens. But I'm only going to be able to get even numbers on this side, right? No matter what I put in front of the water, it's always going to be 2, 4, 6, 8, 10. So I have to get this even over here. So how can I get the hydrogens even?
Put a 2 in front of the sodium
That's right, put a 2 here. Now that's gonna give me 2 NAs. And it's gonna give me 4 hydrogens and 2 oxygens, so I can put a 2 there. Then you can stick a fork in it because it's done. Because that's how you tell if the brownies or the cake is done. You stick a knife or a fork in it. All right. You learned so much in here.
The sad thing is a lot of it's not even chemistry.
All right, so this is just some practice. This is 15, but I don't think we need to do 15 of them to really get the hang of it.
Agreed.
This gave me flashbacks to the little multiple, what were they called? You know the little games that your teacher would have, like the first one that can get all these right, it was like your multiplication tables.
Yeah. Okay, let's just do 1 through 5 just to start with. Okay? So let's just do 1 through 5.
Yeah, we're gonna keep the video going.
Yes. I don't want to have multiple files. So those of you watching this at home, you can, look at the handouts that are downloaded on Classroom, and you can be working 1 through 5 as we are. Don't miss out on the fun just because you're still at home.
I was like, oh, we're gonna ease into this. No.
The oxygens are in multiple places.
So confused. I grew up.
600.
Crap, man.
So that gives you 12.
So you need to get
And
this
the
on.
three is 15. Okay, so you could either do 15 halves or just double everything. That means you need a 2 plus this.
Can we write these on another sheet of paper so we don't have to erase over and over?
Sure.
Kind of work them out.
Sure. quickly go through these. So, this first one wasn't a little bit more challenging, but when we have hydrocarbons like this happens a lot. But we do 6 carbons, I put 6 carbons. 6 hydrogens, I'm gonna put a 3 right there. Now, that gives me 12 and 3 makes 15 oxygens. Well, we can never have an odd number there. Now, you got 2 choices because when we put coefficients, it's going to mean not just molecules, but it can be moles of molecules, so you can have half of a mole or whatever. So you could put 15 halves right there. Okay, that's allowed, 7.5, 15 halves. However, if you don't want to do that, which most of the time we have whole numbers, what do we do to get a whole number? Just times everything by 2, so it'll be 2, 15, 6, and 12. Okay? Does anybody have any question on that one? All right, so now this one, I'm just going to go across the board and I'm going to say I have I4, so I need 4 of these. That gives me 4 sodiums, so I'm going to put a 2 there. That gives me 2 sulfates. Well, I have 2 sulfates and 1 lead. That one's a little bit more straightforward. Now, NH3, and just for the record, you don't really have to know this, but it's a good thing to know since that's such a common compound. NH3 is ammonia. So if you ever hear, someone talk about ammonia or whatever, that's NH3 is what that is. 1 nitrogen, 3 hydrogens, 2 hydrogens. 3 and 2. What's my lowest common multiple? 6. So I'm gonna have to put a 2 here and a 3 there. Now that gives me 2 nitrogens, so I'm gonna put a 2 there. And so now again, okay, this is a 2 and a 3 makes a 5.
5.
So you could put 5 halves, right?
4.
Or do what?
4, 5, 4, 6.
Double everything again. 4, 5, 4, 6. So when the oxygens aren't working out, when it's just the oxygens, just try doubling everything and it'll generally work out. Now here's a polyatomic ion, but it's not the same over there, so we have to kind of do this. 1 iron, 2 iron, so I'm going to put a 2. Okay, I have oxygen here, oxygen there, so I'm going to leave the oxygens to last. And I'm going to say I have 6 hydrogens. Okay, 6 hydrogens, so I'm going to put a 3 here to get my 6 hydrogens. Now that's going to give me 3, and 3 makes 6 oxygens. I have 2 times 3, I have 6 oxygens. Okay, are we good? Are we all good with this? Am I, just boring you because this is so easy, The last one, here, we have 1 hydrogen and a hydroxide, so let's just do the nitrates. I have 2, so I'm going to put a 2 here. You got 1 magnesium, 1 magnesium. Now, what you have to realize is that the H is combining with the OH to make a water. Okay? Sometimes I like to write water as an HOH because it makes it easier to kind of keep track of where everything's going. But the reality is I have 4 hydrogens. So I have to put a 2 right here. That gives me 6 and 2 makes 8 oxygens. I have 6 and 2, 8 oxygens right there. But you can see that there's 2 H's combined with 2 OH's to make 2 HOH's. All right. We could theoretically do the other 10 if you needed to. Those would be yours for your own personal practice. We can just kind of see on that. So the first thing we need to be able to do is write and balance an equation. Now, we'll start tomorrow. I'll give you another one. We're not done yet. I don't know.
I gotta go.
Oh,
Remember?
No.
At the beginning of class, I said I had to get vegetable. Talk about the cold, even though it's not cold.
Yeah, but I probably missed the first part. I probably wasn't paying attention. Okay. Well, this is, it's not gonna be as cold as it's been. Today's a better day. All right, so let's talk now about our different types of reactions. We have 5 general types of reactions. And the first one is called composition. Some call it a combination. It can also be called a synthesis reaction. I like composition because the next one is decomposition. So they just kind of go together. You know, one, you're putting them together. Decompositions, you're taking them apart. So I just like to use those terms because they relate to each other. But a lot of people use synthesis for composition. Your book uses combination. Okay? And it's just 2 things coming together to make one. So we can just say copper solid plus oxygen gas. What's that going to make?
C,
Two things coming together to make one.
C,
Copper oxide. Okay? Now, we have 2 choices. Because you look at copper, it can be +2 or +1. But if you look, the 2 is bolded. Okay, so that means that's the more common oxidation state, is the +2. You really have your choice of picking either one. Okay? But, you forget something? You sure?
Yeah.
I would get it plugged in. Okay, so let's just pick copper 2. So it's going to be Cu plus 2, oxygens minus 2. So it's just Cu up. So I have 2, I need to put a 2 there, and I need to put a 2 there. I mean, if you look at an old penny doesn't have the shiny copper on it anymore. So if I just take a piece of relatively shiny copper and I put it into the fire, there's oxygen in the air. Ooh, look at the pretty green. Okay, again, that's all electrons being excited, being promoted up from the 4s into the 3d, coming back down. Okay? But now what's happening to the shiny copper? Okay? What's happening to it? It oxidized. It turned into that brownish black copper oxide. That's what an old penny is going to look like. It's going to end up having that oxygen. It's a combination reaction. Okay? We'll do this one later on, but we just take hydrogen gas plus oxygen gas. What will that make? Well, hydrogen's what charge, Sam?
Oh, sorry, that makes that +1,
And what's oxygen?
-2,
So the formula is going to be
H2.
H2O, which we know is water. That's how water's made, hydrogen and oxygen. Okay? But I have 2, I need 2, so I have to put a 2 there and a 2 there. Now this is one of the great mysteries of life, because that's a gas, but that's a liquid. How can 2 gases combine together to make liquid water? We already know the answer to this. You just have forgotten. What determines whether a substance is going to be a solid, liquid, or a gas?
How tight tightly held together.
How tightly held together, the IMFs, right? These are covalent compounds, so we're talking about intermolecular forces. Are these going to be polar or non-polar? Non-polar. So what's the only type of IMF that's going to be holding hydrogen molecules together or holding oxygen molecules together? London forces. Now, are those strong or weak? Those are the weakest. And what do they vary with?
Size.
The size of the molecule. These are two very small molecules. So as a result, they only have one London forces, and they only have very, very, very weak London forces, so they have the weakest of the weak. So at room temperature, there's plenty of energy to break the bonds apart, so they stay apart, they're gases at room temperature. What type of IMFs are there between water molecules? Hydrogen bonds, right? And if there's, ooh, let's get hot. If there's hydrogen bonds, that means there's dipole-dipole and London forces, all going to be much, much stronger. So as a result, at room temperature, there's not enough energy to break the molecules apart, and we have a liquid. It's all about attractive forces. Now that's just kind of a flashback to the past, but you know, that's a good dinner conversation. You know, Mom, Dad, just always have wondered, how can hydrogen that's a gas and oxygen that's a gas make liquid water? Just seems crazy. You say, I don't know. You say, well, I think it has to do with the IMFs, that hydrogen and oxygen only have very weak LDFs, but water's got those strong hydrogen bonds, and I think that's the difference. And they're gonna go, wow, our public education is really paying off. Okay? And so you're gonna know some stuff. All right, so composition reactions are just two things coming together to make one. Now, it can be compound plus compound. You're only gonna have to do element plus element. Have any of y'all ever heard of acid rain? Okay, anybody know what element, what major pollutant in coal or whatever that's burning causes or is the main culprit for acid rain? It's sulfur, okay? So come on, follow me. So sulfur is a pollutant in coal and natural gas and oil, okay? So when they burn it, they burn the coal, it gets hot, and then they produce steam to make electricity. But the sulfur also combines with the oxygen as it burns and makes sulfur dioxide gas. This is pollution. Nowadays, though, the coal burning plants, the natural gas plants, in the old days, they had these big smokestacks and they just let it go up into the upper atmosphere and didn't worry about it. But then as we learned more and more about safety and acid rain and different things in the 50s and 60s, well then we started scrubbing and trying to remove the SO2 before it gets into the atmosphere. But some does. Way back in the day. Sulfur dioxide then gets into the upper atmosphere and mixes with more oxygen, using a little bit of the UV light from the sun to kind of give it energy for this reaction, and it goes from SO2 to SO3. Now, we have to put a 2 there and a 2 there to balance it. So notice that that's two elements combining together to make a compound. But now we have a compound and an element, but it's still two things coming together to make one. Then, this now is all up in the clouds in the upper atmosphere. So then it combines with water in the clouds and ends up making H2SO4, which is sulfuric acid, which is a strong acid which people call acid rain. Now, in the United States, okay, so there's the United States, that's Florida, okay? Out here in the Midwest, they had a bazillion coal-burning power plants. They just put all the smoke up into the atmosphere. But the jet stream brings all the weather down and goes that way. And if you ever watch the weather patterns, it always shows things coming this way and that way. Well, so all of the pollution then travels with this, and so this is where all the acid rain. Well, these people out here didn't care about that. Saying, hey, we got cheap coal, we're just gonna burn it, you know. And then, but that's when the federal government had to come in 1978, they made the Clean Air Act, and you had to, that's when you had to really control how much of these things you put up into the atmosphere. So far, nowadays, acid rain isn't quite as big of a deal as it was back in the 70s, 50s, 60s, and 70s. The Adirondacks, which are upstate New York, there's like 200 forests that, or 200 lakes that are totally sterile because of acid rain causing all the marine life to die. But that was back in the 70s, and most of those probably have come back. Anyway, so that's just a whole series of composition reactions. Okay? We'll talk about decomposition reactions tomorrow. But I was actually just reading and learned that they're exhuming Beethoven's body to try and see if there's some kind of DNA that made him such a great musician. And when they dug up his body, they opened up the casket, and he found him in there erasing all of his music that he'd been buried with. And they said, Beethoven, what are you doing? Because I'm just here decomposing.